Lesson 108. In this lesson, we will look at vector equations of a plane and also how to write the equations of planes in parametric form and Cartesian form. So before we begin, we've been learning a lot about lines. So let's compare lines to planes. The question that I have is, how many points lie on a line versus how many lines lie on the plane? So you can think about that, right? So I hope you will say that there are infinitely many points on the line and you can draw infinitely many lines on the plane. Now, how many points are needed to define a line? We know that we need to give the direction of a line, so it takes 2 points basically, right? And how many lines are needed to define a plane then? If you think about that, if I know perhaps like this particular line here on the plane and another line on the plane that is not parallel to the first one that I draw, I can pretty much define, the line has to kind of lie on these two lines. And so it takes 2 lines to define a plane. Okay, so there are some similarities between lines and planes. When we look at the vector equation of a line, we know that we need a point and a direction vector. So on the diagram, I show, point P naught as a given point and M as a direction vector on this line. When we look at the plane, similarly, we need 2 lines. So there are 2 directional vectors, D1 and D2. And I will also need to know the position of this plane. So I need a point or really a position vector, okay, to give the exact location of a plane. So a vector equation for a plane can be found using 3 different sets of given information. It's still possible to find the equation of a plane. First of all, of course, is giving me a line and a point, so that through the point and any points on this line, I can figure out really another direction vector on this plane. The second scenario is having 2 non-coincident and non-parallel lines, like what's indicated in the second diagram. And in diagram C, of course, if I have 3 points on the plane, then I can easily find any 2 or even 3 directional vectors. And then combining those information with one of these points, I will be able to write out the equation of a plane. And notice how a plane is usually labeled as pi. I guess is the letter P in the Greek letter. Okay, so let's start by taking a look at what does the vector equation of a plane look like. So similar to the development of the vector equation of a line, we can make use of a diagram in the XYZ plane space, 3D space. So we have the plane pi here, general point P, XYZ on the plane, and a specific point P naught with components x naught, y naught, z naught on this plane. Okay, so we can write a vector equation relating the position vector OP by adding the position vector OP naught plus the vector P naught P, which lies on the plane. Okay, and then because I know that P naught P, this vector, lies on the plane, so if I have any 2 directional vectors A and B, I can really randomly draw them, like as A here, or like A would be a little guy here. So anything along the direction of A plus anything along the direction of, a smaller vector B. So call that TB. This is a linear combination of these 2 direction vectors. Then I can replace P naught P by their sum. And as a result, I can say that the vector equation of a plane R is equal to R naught plus SA plus TB. Okay, so S and T are just parameters, and R naught defines the position, of this particular plane pi. Writing out in component form or in column vectors, we say that the vector equation of a plane can be written as x naught, y naught, z naught plus S of A1, A2, A3 plus T times B1, B2, B3. If I break it up into parameters, the parametric equations of the plane is x equals to x naught plus SA1 plus TB1, y as y naught plus SA2 plus TB2, and z is z naught plus SA3 plus TB3, just like that, okay? So here we have the vector equation and the parametric equations of a plane. Let's take a look at some examples. First off, we're going to start with 3 points that lies on a plane. We're going to look for the vector equation of it. Okay, so maybe on a diagram, we can kind of like conceptualize what this looks like. So let's pretend this is our plane. And then I know 3 points on it, point A, point B, and point C, just schematically, okay? And so I know that when I need to look for 2 directional vectors on this plane, I can easily pick any pair of these 3 points, let's say AB and AC, and those will serve as the 2 directional vectors. So let's start by finding what AB is. Using B minus A, I have 2 minus 2, negative 2 minus 1, 0 plus 3, which is 0, negative 3, and 3. Okay, this can be simplified into a directional vector of 0, negative 1, and 1. You could use 0, negative 3, 3 as is, but it's just more simple if you kind of like reduce it to 0, negative 1, and 1. All right, so like we said, we also need to find vector AC as our second direction vector. So 4 minus 2, 1 minus 1, 5, plus 3. I have 2, 0, and 8. So once again, I can reduce this. So let's call it the second directional vector 1, 0, and 4. All right. So let me write a note here on the side. So we could use AB and AC as D1, D2 as well. Okay. So going back to writing out our vector equation of the first plane that we have, we only need one of the 3 points. Pick any one you want, okay, as to indicate as the position vector. And as a result, the vector equation is 2, 1, negative 3. I've picked point A, plus S, 0, negative 1, 1, plus T, 1, 0, 4. And that's it. And of course, S and T, if you like, you can include, this statement here. S and T belongs to real numbers. Let's take a look at example 2. So find a vector equation of a plane containing these 2 lines, L1 and L2. So like we said, if we have 2 lines, we are able to find the equation of a line if the 2 lines are not parallel or not coincident, like they're not identical. Okay. So the position vectors of these 2 lines are not the same, like 2, 4, 1 compared to 1, 4, 4. But if you look at the direction vectors, 3, negative 1, 1, and negative 6, 2, and negative 2, what I notice is that the second direction vector is actually negative 2, D1, meaning that we have 2 parallel lines given to us, which is not helpful for finding equations of planes, right? So we need to find a second direction vector. Okay, so let's sketch this out. So the situation we're in is that on this plane, I've got line 1 parallel to line 2. I can use that as one of the direction vectors. So for a second directional vector, what I could do is still having, that direction on the plane, is that I can connect any 2 points. between L1 and L2, and that will form my third, direction vector, so to speak. Okay, and the easiest thing to do is to use the position vectors of these two lines to find our next useful direction vector. So D3, let's call that. All right, so I can do 1 minus 2, 4 minus 4, and 4 minus 1. Okay, so this gives me -1, 0, and 3. Okay, so we can use that. And 2, 4, 1, 1, 4, 4, these 2 points are on this plane because they're on the line. So I can pick any one of those and say that therefore the vector equation of the plane is 2, 4, 1 plus s times, let's use smaller numbers, so 3, -1, 1 plus t times -1, 0, and 3. Okay. And then let's take a look at example 3. A very typical question, right? Does the point for -1 and 5 lie in the plane defined by R? All right. So I think the most straightforward way to do this is really to substitute the point into the line and see if we will be getting any consistent s and t values. Okay. It might be easier for us to first rewrite the vector equation into parametric form. So we have x equals to 1 plus 3s, and then y equals to 0 minus s plus 4t. And then z, we have 4 plus 0s minus 3t, like that. Okay, so I'm going to substitute for -1 and 5. Let's see, so 4 is equal to 1 plus 3s. This implies that 3 equals to 3s, so s is equal to 1. And then substitute -1 as y. I have -s plus 4t. But then I can substitute what I found, s is equal to 1. And if I solve for t using this sets of values, I have -1 plus 1, 0. So t is equal to 0. Okay, so now what about checking? Okay, so what about that, right? So z, we have -3. 4 minus 3t, which is 0. So obviously, -3 is not equal to 4. And as a result, we can say that, therefore, the point 4, -1, and 5 is not on the plane. Okay. Okay, the next thing on the list is taking a look at how we can write the equation of a plane in Cartesian form. Okay. We can start with this diagram that contains point P1 with components x1, y1, z1. And we will say that this point has, or this plane has a normal vector, which is a vector that is perpendicular to the plane, marked as A, B, and C. Okay, and then we're going to say P of x, y, z be a generic point on this plane. And when I form a vector P1P on this plane, well, since it is perpendicular to the normal, the vector P1P dot n must equal to 0, right? Using the property of scalar product. Okay, now let's write out the vector P1P using components. So endpoint is P, so x, y, z minus x1, y1, z1 dot A, B, C, which is the vector n. We have ax minus ax1 plus by minus by1 plus cz minus cz1 equals to 0. I will gather like terms, or terms that will actually have numerical values to it. So separating the variables, I have ax plus by plus cz, and then we got minus ax1 minus by1 and minus cz1. Okay, so that's equal to 0. Recognizing that these terms being subtracted actually carry, actual values, right? They're specific points. So this is actually a constant. And I can call this d, negative d on this side. So when I rearrange the equation, I can write out the Cartesian equation of a plane, which is ax plus by plus cz equals to d. This equation is very handy because you should notice that we have a normal vector of ABC, and that matches with the coefficients of x, y, and z, okay, in this equation of a plane. So here is example 4. Find the Cartesian equation of the plane passing through the point -3, 1, and -7. And it has a normal of 2, 4, and -5. So right away, I'm going to start with the normal. Because that will allow me to write out 2x plus 4y minus 5z equals to d, okay, as a skeleton equation. And then let's substitute the point -3, 1, -7 into this equation. Let's work out the constant d. I have -6 plus 4 plus 35. That's -2, so d is 33. And therefore, we have the Cartesian equation of the plane is 2x plus 4y minus 5z equals 33. Here is example 5. A plane has vector equation. Find the Cartesian equation of the plane. So one thing that comes in handy when we're given the vector equation of this plane is that we know two direction vectors d1 and d2, on the plane, right? So if I kind of sketch this out, here's the plane. I have d1 and d2, and notice how they are not scalar multiple of each other, so they are intersecting. Like d1 like that, and d2 like that. So what's nice about this is the fact that, when I want to turn this into a Cartesian equation, I need the normal of the plane, which is kind of easy to find because the normal must be something that is perpendicular to the plane, meaning that it must be a scalar multiple of the cross product, right, of d1 cross d2. Make sense? Okay, so we're going to find normal by crossing d1, d2. So here we have -1, 2, 0, cross d2, which is 0, 3, and -5. I have a really short bracket here. All right, that's better, right? So either using determinants or using the method by listing out -1, 2, 0, -1, 2, 0, 0, 3, -5. Using either method, right, we can work out the cross product. So -10 minus 0, -10, 0 minus 5, -5, -3 minus 0, -3. So here is the normal, okay? And so this gives us a Cartesian equation, -10x minus 5y minus 3z equals to d. And of course, if you don't like those negative signs, they can all be turned into positive because you just need a scalar multiple. So now sub in a point, 0, -2, and 3, which is a position on the plane. We get -10 times 0 minus 5 times -2 minus 3 times 3 equals to d. I have 10 minus 9 is d equals 1. All right, and therefore the Cartesian equation is, we can fix it, 10x plus 5y plus 3z is equal to -1. Okay, so just make sure you balance the signs. Okay, so lastly, we are going to take a look at parallel, perpendicular, and intersecting planes. So notice now with Cartesian equations, we can also consider directions of these planes using the normal vector instead of its direction vectors. Okay. So if there are two parallel planes, what must be true is that their normals must be scalar multiple of each other. Okay, they have parallel normal lines. So n1 is equal to kn2. If the two planes are perpendicular together, obviously, their normals are also perpendicular to each other. So we can say that n1 dot n2, the dot product, is equal to 0. But if the two planes do intersect at an angle, then we can also figure out, the direction or the angle between the two planes by considering, the cosine theta definition using dot product. So in example 6, we will be comparing the planes 2x minus y plus z plus 4 equals 0 and x minus 2y minus 4z equals 0. Are these parallel, perpendicular, or coincidental planes? Okay, so let's list n1 by listing out really the coefficients of x, y, and z of the first plane. And n2, normal of the second plane, is 1, -2, -4. Okay. So by inspection, we notice that n1 cannot be written as kn2. They're not scalar multiple, and therefore the planes are not parallel. Okay, so we eliminated the first case. Secondly, are the planes perpendicular? Let's dot the two normal vectors. So I have 2, -1, 1, dot 1, -2, -4, 2 plus 2 minus 4. This is equal to 0. All right. And because the scalar product is equal to 0, so let's write this out. Therefore, the planes are perpendicular. Okay. So that's our first lesson on planes.